and we put angular brackets to show that that information about that particular graph, G, is encoded. The string is an encoding of the information about the graph. Now, the actual encoding or representation, we will show how it's done, or one way to do it, on the next board, next session. So, won't mention here. Here we're talking more about the formatting of the description of the algorithm, okay, with its indentation and whatnot, right? So here's the actual language, right? So an encoded description of the graph. So G, and then the property that the elements here have to be members of the set. So G, which is just a graph, is a connected undirected graph. Okay, so that's your language. It's the set of all these strings, and the string encodes or represents information about your graph. It tells you what the graph is. Okay, and your so this here is a high-level description. Remember, it's the third type that we're talking about, previous session. So it's a high-level description of the algorithm, or equivalently, if you like, a high-level description of the functioning of the Turing machine that implements that algorithm. Same thing. And this machine called M, it's a Turing machine M, it decides not recognizes, it decides A. Right? So in other words, there's no looping. This machine M does not loop. It either accepts a string or it rejects it, and that's it. Right? There's no third possibility. It's a decider, not a recognizer. Now deciders are recognizers. Can you see that? If you don't see that, let me try and explain why that's the case. If a machine decides, that means if a string does have the property in the set, the decider will accept it. Okay? Well, that's the definition of a recognizer. Therefore, a decider is a recognizer. The set of deciders are a subset of recognizers. I think that's correct. Okay. All right. So we're giving an example now of a standard presentation, standard description of an algorithm, a Turing machine algorithm. So it'll all be, it's in English usually, all between double quotes, the beginning and the end. Yeah, so M, machine, well, it's an algorithm, so it'll be a Turing machine algorithm. Okay, so we're describing the machine that implements the algorithm. So M's the name of the machine M. So M equals, and then the first line is usually a description about your string, the input string. So the input is angular brackets G, that's this, right? So that's a member of your set A, of the language, okay? So in other words, that's the encoding of the graph G. So you put the information about your graph in encoded form, or the representation of your graph G. Same thing. Alright, so what is the actual algorithm? The step-by-step stuff. It'll typically be broken into stages, numbered. So here we've got, in this algorithm we have 4 stages, numbered, 1, 2, 3, 4. Indented, if needed. For example, 2 is a loop. It goes through a loop and doing something within the loop. And 3, indented, you can see the spaces here and here. 3 describes what's going on within the loop. Okay? So that's why it's indented. And you can keep indenting. You can have loops within loops within loops and so on. And each time you indent, right, you put spaces. So that way you can see the structure of the algorithm. Now it's a pretty standard programming technique. If you've programmed, you'll probably be quite familiar with indenting. Left brackets and right brackets in for loops in language C and so forth. If you're familiar with that stuff from programming, if you've not programmed before, don't worry about what I've just said. Okay, so here's the algorithm. So stage one. So you select the first node of the graph. This encoded G goes into the Turing machine, and the information about the graph G is extracted from that information. It's decoded, right? So the Turing machine knows the properties of this graph G, this particular graph, and then it's able to go to the first node. Now you may ask, this is a high-level description, right? So if you ask a question like, well, how does the machine know which node is the first node? A question like that's lower level. That's more detailed. That wouldn't be considered like high level. So okay, so you find the first node in your graph and you mark it somehow. You mark it, whatever that means. All right. Now you go into a loop, and you just keep going through this loop, doing stage 3. So 2 is like a sort of an outer loop, repetitively looping stage 3. So you need to specify when you stop the loop. So it's a high-level description. Okay. So you just repeat this loop 3, the following stage, stage 3, until there's no new nodes are marked. In other words, all the nodes have been marked, right? So what's stage 3? Well, you have a look at each node systematically, okay, and you mark it if it has a neighbour, in a sense, if it's attached by an edge to a node that's already marked. Okay, so you systematically look at each node, and if it's unmarked, have a look at its neighbours, the ones it's connected to, and if one of those is marked, then mark that unmarked node. Right? And you keep doing that until there are no more unmarked nodes. Okay. Now, step 4 is scan all the nodes to see whether they're all marked. Now, in a sense, you're looking for these G's. It's a set of graphs. And what properties do they have? Well, they're connected. Now imagine you had a disconnected graph. Say you had a graph in 2 parts. Well, you're starting at the first node. You may, all the nodes in one part that included the first node, they'd all be marked, but none of the nodes in the other part would be marked. So when in stage 4, when you do your check to see if, looking at every node, if they're all marked, if you find one that isn't, well, then you reject. Okay? So you're checking, stage 4 is to check that they're all marked. So if they are all marked, we'll accept, and if they're not, reject. So it's either an accept or a reject situation. Therefore, your machine, your Turing machine, is a decider. Right? It's more than just a recognizer. Okay. Now, next session we will talk more about this. How to represent the information about your graph in string format. So we're talking a bit about representation theory. Ciao.